So for today we'll be talking about generating grade code for grade code and universal cycle for weak order, and this is a joint work with some of the undergrad students, which is Marston, Tonga, and Fabio over there. So for today I'll introduce first what is weak order, and then I'll talk about what is grade code and what is universal cycle, and then we'll talk about some strategy on how we can generate these grade code and universal cycles. So first, let's go for what is weak order first. So for weak order, actually, I first noticed about this kind of object because of my personal interest on like horse racing gambling, basically. So when you do horse racing, so for example, when we try to do like a horse racing gambling, so we try to use some of the we can actually use weak order to describe the result of the actual horse racing. So for example, let's say we have 3 horses, for example. So let's say this guy, let's say horse, and then so let's say we have 3 horses, for example, and then so this is horse number 3, and then this is horse number 2, and then this is horse number 1, for example. So to describe the ending result, for example, if the horse 3 run first, for example, horse 2 run second, and then horse 3 run third. So you can describe the result as something like 3, 2, 1, for example, right? But in some of the cases, so another example would be like something like this one, for example, and then so in this case, it is easy to describe what happened. So this one would be like horse 2 will be first place, and then 3, 1, for example. This is just simply permutation. But in some of the cases, for example, let's say this horse somehow run faster, and then now they are on a tie, so they are equal, for example. So in that case, then to describe this stuff is not that easy. You cannot just use simple permutation to describe the result. And in that case, we will use what we call the weak order. So for weak order, basically it is kind of permutation where ties is allowed, basically. So for example, let's say so originally I want to use the horse racing example, but then the school my chair saying my department chair say it is not that healthy. So that's why I use this kind of example. So in this example, what we have here is we have different kind of ice cream, for example. And then so for example, if the vanilla horse, chocolate horse, but the vanilla, chocolate, and strawberry they rank first, then you can rank it in this way. But then in some of the cases, you can say, for example, vanilla and chocolate they rank first favorite, and then the strawberry second, and this is the second way. So basically, we try to study about how many ways we can how many possible ways we can the horse racing can happen, basically, or how many ways you can rank the ice cream in this scenario. Make sense? So that's basically what we call weak order. And so that's actually something I start to get some interest in this topic. And then so in my area, basically it's usually it's about how to generate all this kind of stuff. And then when we generate the stuff, we want to see how we generate the elements such that consecutive string they are different by some small change. And that's basically our work for this around a year, basically. So so we have introduced what is basically a weak order. So for weak order, basically it's like how to rank something when ties is allowed. And so so the next thing I want to introduce is basically how we can represent this weak order. So for example, one way to represent this weak order, for example, like this one, would be something like 3 is equal to 2, which is less than 1, for example. So this one is one of the representation on weak order, which means that 3 and 2, they are tied in the first place. And then 1 will be ranked second, for example. And so for example, similarly, like this one can be represented as 2 is less than 3 and less than 1, for example. That's another way to represent it. So formally, for the weak order, it can be represented as the combination of three symbols, where in between they are basically the symbol like this one or this one. And so you can see that, for example, for all the possibility, they are basically around in here. So for example, this one means 1 and 2 and 3, they are both tied. This one means 1 and 2, they are both first place, and then 2 and 3 is second place, for example. And this one is 3 is the first place, 2 is the second place, and 1 is the third place, etc., etc. But for this representation, we usually think it is not that compact, and so Graham and Dykens basically introduced another way to represent weak order, and which is what we call the high representation. So for high representation, basically what it has is so for the first digit, it basically represents the first horse. Second digit is the second horse. Third digit is the third horse. And so we try to see how many this symbol is in front of a particular horse, for example. So for example, in this case, there's no this smaller symbol in front of 1, no smaller symbol in front of 2, no smaller in front of 3. So that can be represented as 0, 0, 0. This is what we call the high representation. And so for example, in this guy, 1 is 0 because in front of it there's nothing. But then for 2, in front of it there's one smaller symbol. So 1. And then similarly for this guy is 1. Similarly. And this is one way which we can represent weak order. Makes sense? Easy enough, right? So so now the question in our area is generally how to generate all these guys. And usually we are not just talking about how to generate all these guys, but we want to generate gray code or universal cycle for this kind of stuff. So we'll introduce what is gray code and universal cycle. This one is actually one of the applications for weak order. So besides horse racing, there are actually some other application of weak order. And so this one is actually some of the example on how this can be useful. So the weak order actually can be useful in logistics. So basically, it's like how you can pack some of the objects in some of the boxes, basically. So for example, let's say you have some objects in here, for example. So you have like 1, 2, 3, 4, etc. Let's say you have 5 objects, for example. Let's do the easy one. And then now you want to pack the objects. So you have some package in here. For example, you have some boxes in here, and you want to put these objects into the boxes such that there will be no empty boxes. So for example, one way you can do is, let's say you put like this guy here, and then like this guy here, this guy here, and this guy here. And this one can be represented as let's say this is box 0, this is box 1 and box 2. Then this representation can be represented as like a 0, 0, 1, 2, 2. Make sense? And so basically, all the possibility on packaging all these objects into boxes without empty box correspond to all the possibility on the weak order, basically. It's like these two horses rank first, this horse rank second, the same thing, basically, the same idea. And so this is usually used in like logistics to describe how they put the cargo into the ship, and they are also useful in like, actually this is something I found out recently. They are used for genome, try to analyze the genetic stuff, basically the DNA stuff, because they try to like pack some protein together, and that's basically one of the applications. And horse racing, obviously, and so that's basically some of the application for this stuff. So far, okay, right? So as I mentioned in my area, what we usually do is we want to study about how to generate all the objects in the in a particular set. So in this project, basically what we are trying to do now is we want to generate all the possible weak order in weak order, basically. But in my area, besides of generating other objects, we usually deal with what we call the gray code. So for gray code, what it means is that we want to generate each of the object such that each of the objects appear exactly once, and for consecutive objects, they are different by 1 bit, or they are different by some small changes, small amount of changes. So for example, let's say this is gray code first. So this one is simple. Let's say for example, we want to talk about the set of linked 3 binary string, for example. So this one is a simple generation which you generate all the string in lexicographic order. So for example, this is 000, 001, 010, etc., etc. But this one is not what we call gray code. So for gray code, it means that we want to generate all the strings such that they are different by some small changes. So for example, this one is what we call gray code. So for gray code, what it means is that if you look into the consecutive string, they are different by just 1 bit change. So for example, like this guy and this guy, they are different by 1 bit change. This guy and this guy, they are different by 1 bit change, etc., etc. And this is what we call gray code. And should I go over it? And so let's go over this one. So this one is also what we call gray code, and this is actually something we call universal cycle. So for this one, for all the consecutive strings, they are different by 1 shift and at most 1 bit change. So for example, like this one and this one, they are different by 1 shift, which you shift this guy to the back and then change to 1 bit. This one and this one, they are different by 1 shift. So let's say you move this one to the back and then become this one. This one and this one is like you move this one to the back and then you change it to 1. So and this is what we call universal cycle, which we'll introduce in a second. Why this one is so useful.
So did you sum up the third digit and the plus 1? Take a plus and
This one, I think it's not generated in that way, but this is actually one way to generate the universal cycle, but there are multiple ways you can do it. So they are basically different by 1 shift and at most 1 bit change. So sometimes you can do it in that way, but there are multiple ways you can do it.
Does the change have to happen at the last?
Yeah, have to happen at the last.
And
it must happen at the last.
And is it the circulus and circulus equal to?
Yeah.
Oh, okay.
So maybe let's go over the universal cycle stuff, and then we'll talk about the gray code in the later part of this talk. So the first one I want to introduce is what we call the universal cycle. So for universal cycle, basically it is a complex string which will consist of each of the substring, each of the elements of the set as a substring exactly once. So for example, let's say when we talk about the set of linked 4 binary string, then this one is a universal cycle for the set of linked 4 binary string. So how does it work? It's basically if you look into each of the substring. So the first one is 0, 0, 0, 0, which is this guy. And then when you shift it, then it says 0, 0, 0, 1, and then 0, 0, 1, 0, and then 0, 1, 0, 0, 1, and then this is 1, 0, 1, 0, etc., etc. And then this string is circular. So when you go to the end, that will be, you will get 1111, 1110, 1100, and 100. So if you look into the successive string in this sequence, basically, for each of the successive string, they are different by 1 shift, and then at most 1 bit change. Basically, it's like you shift it, and then this bit can be 1 or 0, basically. And so that's 1 bit change, basically. And so this one is actually a pretty useful sequence because you basically pack each of the elements into this sequence. And it's the shortest possible sequence that consists of each of the elements in the set. And so usually this one is useful for like pseudo-random number generation, which is actually the proposal I get for the NRF. And also it is useful for the encoding, error correction, stuff like that. So in this area, the question usually you have is for a particular set. So this one we know we have for the set of linked 4 binary string, or length n binary string. But then now given an arbitrary set, so for example, the set of weak order, the set of permutation, for example, is that possible to construct a universal cycle for the particular set? And so that's usually the first question. The second question will be, if it is possible, then how we can generate them, how we can construct them. And then third one will be how we can construct them efficiently. And that's basically the stuff we usually study in this area. So this one is basically some of the work I've done with one of my undergrad students. So before that, when we talk about weak order, actually we know that weak order, the universal cycle for weak order actually exists, which someone had proved it already. But actually the more difficult question is how to construct it. And this problem actually was never solved. And then it was actually posed on an open problem on one of the research and open problem on Greco, which is a paper which posed an open problem on that. And so before that, no one solved it. And actually, this was solved by one of my undergrad students, which we developed a very simple, intuitive, greedy algorithm to find the universal cycle for the set of weak order. And the idea is pretty simple, which is actually quite nice. So the idea is the approach is what we call greedy approach, which means that you greedily try to get the maximum, or you greedily try to get the minimum, stuff like that. So the idea is basically work like this. So you start with this weak order, which is all 0, which means all ties. And then now every time, this is called preferred larger. So for preferred larger, what we do is every time we try to append the largest possible value such that the resulting sequence, the resulting word is a weak order, and then the resulting word has not been appeared before. And so you just keep doing that, and then eventually you will be able to generate the preferred larger sequence for the weak order, which is a pretty simple, intuitive algorithm, but then it works pretty nice. So let's see how this one works. So for example, at the beginning, you start with something like this one. So you start with all 0. And then now you try to greedily append the largest possible value if that is possible. So you try 2, which now 002 is not weak order because for 002, it should be represented as 001 according to the height notation. And so this one is invalid. And then so you try 1. And then so 1, it works, and then you put it there. And then so you move on. So now you try the largest one, which is 2. And then so for 2, it doesn't work again. It works in here, so you put 2. And then you move on. Now if you put 2 in here, this one is an invalid word. So because it should be, you always have a 0. You will always have someone ranked in the first place. So in that case, then this is invalid. And then so you try another one. Try 1, and it doesn't work. And then now you put 0. And then so similarly, you put this one doesn't work because the valid one should be 201. You cannot have both of them to be third place. That's invalid. So you put this one. And then now you try this one. This one actually is a valid weak order. But the thing is, it has appeared here already. So for weak order, for universal cycle, each of the string appear exactly 1. So you appear twice in here, so that's not work. And then so you, this is invalid. And then you try this one. And then so you keep doing that, and eventually you can generate all the whole universal cycle. And we prove that it will work for all the n, basically. Which is a pretty nice result, which is a super simple, super intuitive. But then it allows us to construct the first known universal cycle for the weak order, basically. Does it make sense? And so that's basically one of the results which I work with Marston and on generating the universal cycle for weak order. And actually not just that, he actually divides two universal cycles. The first one is this one, what we call the preferred larger. This one is what we call the preferred opposite, but it is similar. So it's just the greedy strategy has a little bit changed. So for this one, the greedy strategy is now you are always trying to increment. So you are always trying, so similarly you start with this guy, but then now you are always trying to increment by 1, not trying to get the maximum value. You try to increment by 1. If it doesn't work, increment by 2. And then if it doesn't work, increment by 3, etc., etc. And then you take the modulus on n, basically. So for example, like this guy, 1, and then now what you try to do is you add 1 on it and see if it works. So it becomes 2. And then, so 2, and then you add 1 become, because we take modulus 3, so it becomes 0 again. And then if you keep doing that, it will allow you to generate the next, generate a new universal cycle for this stuff, for this record, basically, which is a pretty nice result because it is so simple, but then it is so simple, intuitive, and then it kind of works, basically. Makes some sense? Yeah. So so that's basically one of the work which I work with some of the undergrad students on how to generate this universal cycle for weak order. And so there are actually an open problem in here. So for this method, this is what we call the greedy approach. So the greedy approach, usually the advantage is that it has a pretty simple intuitive method, which allows us to understand how this one works. But the disadvantage is that usually it is inefficient. So in terms of efficiency, we talk about how efficient in terms of memory and how efficient in terms of speed, for example. So for this approach, actually, it is not that efficient in terms of memory or in terms of space. Because now, let's say, for example, when you want to generate the universal cycle, let's say you are, at a point in here, for example. You basically need to memorize all the previous string to see if they have appeared or not, right? And so in terms of memory, basically you need to memorize the whole set, or you basically memorize the whole weak order stuff, basically. So the memory or the space which we take in this approach is exponential, which means that, for example, if you want to generate universal cycle for, let's say, n is equal to 1,000, likely it won't work because it will be like for n equal to 1,000, the number of weak order will be in the order of something like this one, which is super large. So the next question actually is how to generate a way to efficiently list out the universal cycle, or how to efficiently generate a universal cycle for weak order. And so the problem actually, how to efficiently generate universal cycle for weak order, is actually solved by my teacher and me, basically. So that is a little bit more complex, so that's not undergrad research. And so we actually devised a nice efficient algorithm to generate universal cycle for weak order. But the universal cycle is different from the preferred larger and the preferred opposite sequence. So the open problem in here is basically how we can efficiently construct the universal cycle for this guy and this guy, which is not known yet, actually. I mean, actually, I'm working in my office today to see how I can efficiently generate this one. But it is still not known. It is open right now.
Why do you need exponential memory? Can you just search for any n consecutive letters that appeared before?
So
the number of weak orders is exponential.
The number of weak orders is exponential.
Oh,
so basically, like, let's say, for example, let's say this string is exponential long. Can be, let's say, n is equal to 1,000, for example. This will be super long. So if you look into the previous string, it will be yeah.
Thanks.
Yeah. So that's why we cannot do it. I mean, we can do it, but I mean, when n is large, then we cannot do it. And so that's actually one of the results when I work with one of my undergrad student master on how to generate the universal cycle for weak order. Any questions so far?
You're saying that that's a problem.
Yeah, this is open problem. How to efficiently generate the preferred larger and preferred opposite is open. We have a way to efficiently generate a universal cycle for weak order, but it is not the same as these two guys. It is different.
The way of generating this code, but then you're trying to do it efficiently.
Oh, so you have a method For different order.
Yeah, a different order, a different universal cycle, which is we just published on Discrete math. But I mean, the mechanism is much more complex. This one, the nice thing is that you see the algorithm is super simple, super intuitive.
Yeah.
But I mean, the algorithm I work with my supervisor is much more complex. It is efficient, but it is much more complex. So it would be nice if we can find a efficient algorithm to generate these two guys, which is something still open.
So the other algorithm doesn't require exponential.
That one is order of n. Order of n in terms of space, order of n in terms of speed, which is super efficient. So let's say n is equal to 1,000. This is doable, something. But like exponential, n is equal to 1,000. Even supercomputer is not doable.
So the n running time is like when you generate one more digit,
One bit.
all of n.
All of n, yeah.
Is that big O or little O?
But
Big O.
big O. So let's move on to the next thing. So the next question we have is so now we talk about universal cycle. The next result is basically just on gray code. So so what we want to do is basically similar to here. Maybe I should introduce how we generate this one first. So this one is what we call gray code, right? So for gray code, basically for each of the consecutive strings, they are different by 1 bit. And actually, there's a very simple approach to generate this gray code, and this is what we call the binary reflected gray code. So the question here is, let's say for example, we want to generate B4, for example, B3, for example. So B3 means the set of binary string of length 3. So there's a very simple way to generate the this gray code, which is called the BRGC, which is a binary reflected gray code. So let's see how this will work. So at the beginning, it is something like this one. This is called BRGC1. So this method is recursive. So this one is called BRGC1. So BRGC2, how it works is like this. So first you get this copy and put it here, 0, 1. And then you prepend 0 on it. And the second step is that similarly, it's the same strategy. You take this thing, put it here, and then prepend with a 0. And then you reflect it. And this is what we call BRGC3, which is super nice. And the nice thing about this one is that for each of the consecutive strings, you can see they're just different by 1 bit. So like this one, we can prove this by induction. So basically like this is different by 1 bit, and then you do the reflection. This is basically the same thing, different by 1 bit. And so for all the consecutive strings, they will be different by 1 bit, which is super nice. So now the next question we have is how we can similarly generate a gray code, like something like this one, which they are different by some small changes for the set of weak order, which is the second question I give to my students, and they actually have some nice result, which is we are able to generate a new gray code for weak order, basically. So for this problem, actually, it is kind of solved before, actually. So in the 1984, some of the guys, they developed a way to generate them in lexicographic order. But for lexicographic order, it is not in gray code. But the problem actually was solved by this guy, Baril. And so what he does is he proved that one gray code does not exist, but then two gray code exist, and then he is able to develop an efficient algorithm to generate a true gray code for weak order. And so this one, for example, is one of the example on the two gray code, which you will see that for each of the consecutive string, they are differed by 2 bits. So for example, like this guy and this guy, they are differed by these 2 bits. This guy and this guy, they are differed by this bit, at most 2 bits. So sometimes maybe 1 bit. And then this guy and this guy, 2 bits. This guy and this guy, 1 bit, etc., etc. So for all the consecutive string, they are differed by 2 bits. And so it is a pretty nice result. But as far as up until now, there's only one way to generate the gray code, which is this way. And the gray code is also not cyclic. So by means of cyclic, it means that the last one and the first one, they are differed by more than 2 bits. And we want to have a cyclic gray code, which means that the last one and the first one, they are also differed by small amount of changes. And so that's why we try to work on these guys, work on this problem. And then the nice thing is that we are able to devise a new algorithm to generate gray code for this weak order. And the idea actually is something that is an extension on what we do in here, basically. We try to basically extend this algorithm to generate gray code for these guys. And so let's see how this one works. Maybe I should go over this one first. So the big idea is actually quite simple. So the big idea is actually we want to focus on just generating the increasing weak order. So by means of increasing weak order, it means that it is a weak order where the string is for each of the, let's say this one for example. So for each of the symbol, they must be larger or the same as the previous symbol, and that's what we call increasing weak order or increasing string basically. So for example, for all the weak order, if it is increasing, these are the only 8 increasing weak order for n equal to 4. So for example, you will see that for each of the symbol, they must be larger than or equal to the symbol before. So the big idea is first we try to generate a gray code for these guys, which is the increasing weak order. And then second, once we have this representation, the second step we try to do is basically we try to permute them to generate the rest of the weak order, basically. The idea is basically like that. So these are basically the representation. And the next step is that we try to permute the symbol. And so for example, when we have 0, 1, 1, 2, we can try to permute them to have like 0, 2, 1, 1, 0, 1, 2, 1, 0, etc., etc. We try to permute them, and then eventually to list out all the possible weak order. And that's basically the big idea. And so the first step is how to generate this stuff, which is an increasing weak order. And it turns out that there are pretty nice extensions. We can actually use this BRGC approach to basically generate this increasing weak order. So let's see how this one works. So this one, first, how we can generate this BRGC thing. There are actually a construction tree or a recursive tree to generate this stuff. So you can think about, let's say we have let's say, so we try to build a construction tree. The tree has 2 components. First component is something like this one. So you have a plus sign. So if it is a plus sign, then it will generate two components, which is 0 and 1. If it is negative sign, then it will generate this guy, 1 and 0. So now we can try to use this tree to basically try to construct this BRGC thing. So the way it works is that first it starts with this guy, which is a plus, and then it will generate, this is plus, minus, plus, minus. It will generate this guy 0 and 1. This is plus and minus. Makes sense? And then now this is plus, then you basically move this component in here, move this part in here, then give you like this one. Similarly, for this one is minus, so you move this component in here. And then similarly, we have to do one more step, which is this one. So plus, we put in here. And then minus is something like this one. This is plus, so we have this one. Something like that. And then if you list them out the string, 0, 0, 0. This is 0, 0, 1. 0, 1, 1. 0, 1, 0. 1, 1, 0. 1, 1, 1. 1, 0, 1. 1, 0, 0. And this is exactly here. And that's basically one of the ways to generate this BRGC thing efficiently. And so now we use this same strategy to try to apply to this guy, but with a little bit modification. So, sorry. So the set we are going to generate is this one. So increasing, let's say increasing weak order, which is something like this one. 0, 0, 0, 0. So the set we are going to generate is basically consists of this guy. But now we try to consider a representation of all the elements of this set. And so we consider this set. So this set, what it does is basically we put all the 0 at the back. So let's say this one is the same. So let's say this one. But now this one, what happens is that we put the prefix, which is 0, put it at the back, which will be something like this one. Make sense? So we basically just rotate the string and then to put the 0 at the back. This one, we rotate the string and then put it at the back, become like this one. This one is something like this one. This one is something like this one. And then and our goal is basically to generate this one. Basically, they have a one-to-one correspondence for each of the string in here and here. Basically, you just move the 0 at the back. And this is for the manipulation of the tree, basically. So now the tree will have 3 types of nodes. First type is something like this one. So if you have a 0, they just have one children, 0, and they will be n. The second type is something like this one. You have a plus sign, and then you have a value t, for example. Then this guy will generate 3 types of children. 0, t plus 1, and t. So this is plus sign, this is a negative sign. The third type of tree is basically, third type of node is this one, t minus. And then you generate t plus 1, t, and 0. And this is plus and minus. And then you try to start the same thing. So at the beginning, you have 0 and 1. This one is plus sign. This is don't care the sign. So for 0, it always just put 0, basically. So why when we have 0, it always 0 is because in here, when we see a 0, you know that all the suffix is going to be 0. And so that's why when we see 0, then we just give it a whole bunch of 0. This guy plus sign, then what we try to do in here is first you generate 0. Then this is 1, become plus 1, then 2. And then 1 in here, basically, and plus and minus. Then this guy is 0 again, 0 again. This one plus sign, similarly, 0, 3, and then 2. This one, 2, and then 1 and 0. So you see that the nice thing about this tree is that when they are neighbor, they basically carry the same value. And that's something we proved that when you construct in this way, when you have 2 roots, they they are neighbor with each other, they are always carry the same value basically. And so now when you print the stuff, the last bit must be 0 basically, because for weak order, the last bit basically must be 0. You always consist of a 0 for weak order. Always consists of a people or a host who rank first. So there's always a 0. And so now if you list out the string, then this is basically 0, 0, 0, 0, 1, 0, 0, 0, 1, 2, 1, 2, 3, 1, 2, 2, 0, 1, 1, 2, 0, 1, 1, 1, 0, 1, 1, 0, 0. And these are basically the 8 components, the 8 elements in here. And the nice thing is that if you look into these guys, they are just different by 1 bit change. Like this one, this one, this one, this one, and this one. And so that's the basic idea or the foundation on how we generate a gray code for this recorder. Basically, first step is to generate gray code for some representative of this increasing recorder. So once we have these guys, then it is much more easier because for the multi-step permutation on how to generate the multi-step gray code for this multi-step permutation, there are like thousands of algorithms to do it, basically. Maybe 100 algorithms to do it. So this is actually much more easier. The most difficult part is basically how to generate these guys. So once we're done, then the next thing is basically we just apply some of the common algorithm to generate gray code for just multi-step permutation. Basically, you have to basically just permute them such that they are a true gray code. So now between them, it is one gray code, and then between the listing, it is two gray code. Now when you join them together, then you form a true gray code for this recorder thing. And the nice thing about this one is also that for this one and this one, we can prove that actually they are different by 2 bits. And so that's why this gray code is also secret. So the last string and the first string, they are also different by 2-bit change, which give the nice property, which is actually the first secret gray code for the weak order, basically. So this is what we do basically in here. So we first generate this. This one is I think it's that one. Then we try to permute them to generate the gray code for each of the listing. And then now we try to switch the column such that the last string of the listing and the first string of the listing, they are different by 1-bit change, which are basically in here. We just somehow switch the column and then join them together. That's the gray code, which is a pretty simple, but then it is quite a pretty simple and intuitive method, but then it works pretty well. Questions so far? So the nice thing is that for this algorithm, we actually extend this BRGC algorithm to generate the weak order. And the BRGC algorithm is actually pretty efficient. It is in cat. So this one cat means constant amortized time. So it means that for each of the object, we can generate in constant time, basically. And so because so we use this framework to generate the weak order, and then we show that actually to generate the weak order, we can also generate them in constant amortized time, which is basically the best possible in terms of efficiency. And so that's actually the second work we work on the weak order stuff. So the other thing actually, which is nice, is that somehow we found out that this algorithm can extend to generate other combinatorial objects, to generate gray code for other combinatorial objects. And so the other combinatorial object which we are working on is actually this permutations and also Ballot sequence, which we proved that by using the similar idea, we can actually generate a gray code for Ballot sequence. And Fabio, do you want to come and talk about it?
Is it okay?
Okay, so let me so one of the works that we're doing right now, this summer, and kind of this is a sneak preview of the future paper we might publish, kind of. But is generating what is called ballot sequences. Ballot sequences came up in around 1878, where there was a question posed of what is the probability that if you have, let's say, a candidate A and a candidate B in an election, what is the probability that throughout the vote counting, candidate A is always winning over candidate B? So ballot sequences are defined simply as binary strings where the number of occurrences of 0 is in any prefix is strictly more than the number of occurrences of 1. To give an example, for example, 001, this is a valid ballot because there's more zeros than 1. If 011 is not valid ballot because the rule is basically there can be equal or less ones than 0 in any point of the prefix. So to illustrate even better, say you have 0, 1, 0, 1, 0. This is valid ballot because at any point in the string, if you cut it, there is larger or equal number of consecutive zeros than 1. This, for example, in the same construction, wouldn't be valid because here in this prefix there's more ones than 0. So before, so when we got into kind of trying to find some extensions of this algorithm, we tried to think about how to generate ballot sequences, and up to now there's only been one paper that covers how to generate generalized ballot sequences, meaning ballot sequences that don't have to be binary. So something like this is valid ballot and generalized. Basically a KRE ballot sequence. There's only one paper that covers how to generate in gray code. Sorry, because we deal mostly with gray code in our research. And so our idea so far is, like Dennis said, extending the binary reflected gray code. As Professor Dennis kind of introduced earlier, in the binary reflected gray code approach, you first take the previous n generated sequence, you copy it, you prepend a 0, then reflect it, and then prepend a 1, right? For our approach, what we're doing is appending instead of prepend. So the valid, say, ballot of 1 is this guy because you cannot have a 1 without a 0 before, right? So what we're doing is, for our approach, we first copy it and try to append a 1. If it's valid ballot, then we have it there. And then we reflect it. In this case, it will be 0 again. And we append a 0. That is the main idea behind our approach. Let's do it for n equals 3 to illustrate. Say we copy first, and here we try to append a 1, but this will no longer be valid. Valid ballot. So we don't generate the string, and we append a 1 here. Then we reflect, and we append a 0. Basically, append a 1 when possible first, reflect, and then append a 0. In order to do this, we're using a generating tree that looks something like this. Basically borrowing the same idea from the previous recorder algorithm. We start with the nodes 1 and 0 with positive and negative signs. And if you have a positive sign, you generate 1 and then 0. So you're gonna have 1, 0. If you have a negative sign, you're gonna generate 0 and then 1. This is a little bit different. And the signs are gonna be positive, minus here, respectively. For say, for example, for n equals 4, we're gonna have and this will be so the way we create the tree, the basic strategy is the same. We only have to take into consideration that at any point we don't generate an invalid ballot. We do this by counting the number of total ones and also the number of consecutive ones to ensure that we have at least the same amount of consecutive spots before for zeros. So the bottom level of our tree is always going to be 0 because ballot has to start with 0. And basically this tree, if you traverse it down up, gives you the sequence for this is n equals 4. So this will be 0, 0, 1, 1. This will be 0, 0, 0, 1. This one will be 0, 1, 0, 1. This one will be 0, 1, 0, 0, etc. 0, 0, 0, 0, and then finally 0, 0, 1, 0. Yeah. It's too bad I erased n equals 3. I think again. So using the strategy on this thing, we can append yes, reflect. You see, this one is the same as here, the same order. So that's how we're trying to generate the ballot sequences for an arbitrary n in gray co-order, in 2 gray co-order. The only paper published before only covers 3 gray codes. So we're trying, our approach generates 2 gray code, which might be advantageous. And that's basically it.
Any questions?
I have a question. So is there so does number of universal cycles for weak order is known? At least asymptotically.
So I think it's not known yet. So if it is for the set of binary string, it is known. Basically, you can actually the universal cycle is correspond to a Eulerian path of a corresponding graph. And so basically, you need to just count how many Eulerian paths there are. And so that's how to calculate the universal cycle for binary strings. But for weak order, I think it's not known yet. Which is maybe a nice problem to work on.
Okay, so my second question is that, so as far as I remember, there was a slide of the on the existence of universal cycle. So the result by Horan and Herbert.
Yeah, Victoria.
Yes. How do they prove that there exists a universal cycle?
They basically try to construct the graph for the we call the universal graph, and then they try to see if it's Eulerian. So if this is Eulerian, then they show that it's Eulerian, and then so there is a universal cycle. But then how many of them? I think they don't have the result yet.
Is it really corresponding to Eulerian circuit? I was thinking that maybe correspond to Hamiltonian cycle. Because vertices may represent one code, one.
Yeah. So for this universal cycle, there are two types of representation. One type is they call it de Broglie graph. De Broglie graph, which is basically for each of the vertex, they correspond to the prefix, not just the all string, but just the length n-1 prefix. And that one is the Eulerian graph. Eulerian graph.
Okay, I see.
Otherwise, then would be the Hamiltonian graph.
Alright, that would be harder.
Yeah, Hamiltonian graph is a lot harder, so that's why they try to find an Eulerian graph instead.
So their construction only deal with a small portion of universal cycles or the whole question? I mean, so do their construction covers all the universal?
They don't have a construction. They just show that they exist. But then the open problem actually is how to construct them.
Okay.
That's what they put in there, and then we construct one of them. Actually, two of them. Any other questions?
If I give you some let's say we have for the second problem, like for the gray code.
Yep.
If I give you like some substring, like for instance in this case, if I give you four numbers, can you generate next one easily, or do you have to go through
That's an interesting question. So for this strategy, we cannot do it. But there is another strategy which is called successor rule approach. So this one is more like a recursive approach. And the bad thing is that
of this data.
yeah, so you don't know we don't know the position of it unless you have a ranking algorithm. But then for the successor rule approach, basically it's like you have a simple rule which you say the next string is something. And so that one is a nice thing which allows you to generate the next string when you are given a particular string. And actually the work this work which I did with my supervisor is actually a successor rule approach to generate a universal cycle for recorder. So what we have is basically you are given an arbitrary number, arbitrary recorder, we can generate the next one by using the successor rule. So this one, but it's just much more complex, so that's why I don't want to go over it today.
Yeah, but it's much better, right?
But it's not that easy to cover in like 15 minutes. It's not that easy. This one is much nicer because it's intuitive, simple.
Any other questions? If not, let's thank the
Thank you
speaker again.